just so everybody knows we are recording. This will get added to ECC University so that you can review this course at any time. We'll also have the attendance quiz that will accompany this course on ECCU. I'll send a link to that in the chat as soon as we wrap up this session today.
Thanks, Sally. Yeah, my name's Jeremy Mitchell. I'm a senior geophysicist with our Munitions Response Division, and today we're going to be going over a brief overview of ground penetrating radar and safety. This image here shows an active project on Wake Island where we successfully conducted a GPR survey to locate an existing pipeline. If there's any questions, feel free to jump in, unmute, or raise your hand. I'll try to monitor. I've got a few different screens here, so or if you want to wait to the end, that's fine too. So today we'll be talking about ground penetrating radar and how it works. Just kind of a high level overview, as well as what GPR can detect and some of the limitations, how we can use GPR to increase safety, and then what we should know as contractors when we're going to perform a GPR survey. And then any questions at the end, of course. So how GPR works. The image on the left is an example of an ECC-owned GPR system. And when I refer to the system, I'm talking about all the individual components that make it up. So the control unit, which is kind of the brains of the system, the battery source, and then the sensor, which is comprised of a transmitter and a receiver. And then there's the optional external GPS in the event that we want to collect data for post-processing. So a big distinction, this is a non-destructive testing method. So this image here on the right kind of shows a 2D representation of what's happening. So as you push the antenna across the surface, there's a transmitter that's emitting electromagnetic radar pulses. Those pulses travel uniformly through the subsurface until they meet a different type of material. When that happens, it's reflected or refracted off of that material back to the receiver, which is then interpolated by the control unit. This slide is intended to show the different form factors for GPR. Not every GPR system looks exactly the same. The image on the left here, we did a ground penetrating radar survey out in Guam on Andersen Air Force Base. We were locating subsurface utilities. This top middle image shows a concrete scanning system where they're mapping out the concrete reinforcement. And then again, this Wake Island photo, which is a more compact version, easier to travel with, which is why we chose that for Wake Island. And then this bottom image is an example of a towed array system. I built this custom system for a project a few years ago in Colorado. And that was just to speed up the survey. This slide here is intended to show that we have some resources available to us before we even step foot on the site to evaluate the effectiveness of GPR. So this image, it's a little bit grainy. I apologize for the resolution, but the intent here is to show that the USDA publishes a map called the Ground Penetrating Radar Suitability Map. The way that you can interpret this is anything in green is really good for GPR and anything in purple is unsuitable for GPR. So, looking at the green, some things stand out. Just for example, here in Nebraska, we have the sand hills. Dry sand is excellent for ground penetrating radar depth and resolution. Whereas clay, like wet clay soils like we find in North Dakota, are unsuitable. And the reason for that is this chart on the right here. Every material has what's called a dielectric constant. And I'm not going to go into the specifics, but just generically, you can think of that as a material's ability to store energy. So you can see air has a constant value of 1. which GPR radar waves travel really fast through air, whereas the opposite is true for water, which has a value of 81. So you can kind of see here the difference between a dry clay and a wet clay. Dry clay is okay. Wet clay, typically you get really poor depth penetration and resolution. And the reason for that is that radar wave is being attenuated or slowed down by those water molecules. So I just show this because if we want to, conduct a GPR survey, we have some tools that we can use to kind of assess the effectiveness before we even get out there. So how GPR works continued. This image here is kind of showing you what the GPR operator is seeing as they're collecting and interpreting data in the field. So as you push a GPR sensor across the surface, you're creating essentially a 2D cross section of that line path. We call these radargrams. So this image here is called a radargram. And the way that you can look at this is your distance is this top, left to right. And then you have depth information from the top down. So as you're crossing over, say, for example, we have three pipes here. As you cross these, you get what's called a hyperbola shape if it's detected. And that's basically just an upside down U-shaped reflection pattern, which is pretty consistent with a utility. But there is some interpretation that goes into this. It's not always easy. You can see this is kind of a confusing image to look at if you've never seen one before. The other complicating factor is, sometimes you have utilities on top of each other. So it's important that we, have someone qualified to interpret these data sets, these radargrams, to make sure that we're accurately locating all the utilities on a project site. Here's some examples of what GPR can detect. This is not an exhaustive list, but it is, maybe some of the more common features. So metallic utilities, of course, non-metallic utilities we can detect. However, the distinction there is these are oftentimes more difficult than metallic. So GPR relies on a contrast to detect things. So metallic utilities show up really good because the contrast between metal and, say sandstone, for example, is pretty great, but a PVC pipe may not be as easily detected. And then concrete reinforcement. This is pretty common in the GPR industry. Oftentimes, contractors need to know where they can core drill or saw cut safely to avoid, cutting through rebar or post-tension cables primarily. There's a lot of safety concerns surrounding post-tension cables. Beams, wire mesh, you can get some slab thickness information as well as moisture intrusion and cracks. And then for geotechnical and soil features, such as voids, sinkholes, you can get stratigraphy information. If you need to find fill material boundaries or depth to bedrock information, as well as utility trenches. And then for some of our environmental and archaeological surveys, that might refer to an underground storage tank survey, buried drums, septic tanks, even graves or buried debris, foundations, and then cultural artifacts. And then I have this image here of the uniform color code. I'm assuming that most all of us have at least some understanding of this, but we really should be able to interpret the markings. So if you're not familiar with these color codes, I encourage you to review this for your project sites. And then just some of the common surface markings that we use are spray paint, flagging, wooden stakes, ribbon. And then for concrete, sometimes we'll use markers or tape if we can't make permanent markings. So these are all things that we can discuss up front if you ever need a GPR survey on what your preferred marking method is. This slide here shows some real life examples of GPR in practice. So I took this photo, this top left photo of a concrete scan that I did for a client who simply needed some safe locations for core drilling. So I just mapped out the reinforcement within the concrete slab itself, gave them some safe locations for that. This top middle image, this is an example of a three-dimensional GPR survey. So this client had an asphalt parking lot where water was seeping through the cracks in the asphalt. So I went out there, we determined that there were no water lines in the area, which kind of confused us at first. So I decided to do a 3D survey, which consists of laying out a 3D grid, collecting data in both the X and the Y direction. And then that data is taken to the office and post-processed. And what we determined was the way that you can interpret this image is everything in red is competent asphalt. And then in the middle here, you can see this blue and green. That's where the water intrusion was taking place. And so I did a little bit more digging, and it turns out that there was an intermittent stream that historically had ran through this site, kind of north-south here. And so this particular year happened to be one of the rainiest in several decades. So this underwater or underground stream had reemerged essentially, and that's what was causing this issue. So we used GPR to kind of delineate that problem area. They were able to excavate and mitigate that. This image on the right, this shows a really great example of good GPR data showing underground storage tanks. You can see very clearly those hyperbola shapes, super easy to interpret. You can mark those out and excavate safely. This bottom image, this shows an example of what a sinkhole looks like. You can kind of see the dipping of the individual layers, subsurface soil layers. Where this may be important is, say for example, you've got a project site where you're not even going to excavate, but maybe you need to bring in heavy equipment such as a crane. You want to know that the subsurface conditions can support that weight to avoid any injuries or safety issues on that site. And then this bottom right image, this is kind of a more somber project that I conducted for the Southern Ute Indian tribe in Southwest Colorado. They had hired me to come out and try to identify the location of a mass burial from the internment camp days. So this image here shows me actually calibrating my system to a known grave, and we ended up finding the mass burial, this back area over here. So some of the GPR limitations, again, GPR is not a magic device. It cannot detect materials by type. You can't program it to look specifically for a PVC pipe. It only can detect materials by contrast. So the greater the contrast, the better your odds of detection are. Wet clay soils, we can just generally assume that you're going to have poor depth penetration and by default, poor resolution in the data set. For deep, small targets, a general rule of thumb, sort of, for utilities is you need 1 inch diameter per 1 foot of depth. So, if you're looking for a 3-inch pipe, maybe you can see that reliably down to 3 feet. There's a lot that goes into this. So, it's a general rule of thumb. A geophysicist or GPR operator may be able to look at the site-specific conditions and give you a better estimate. But if you just need a general rule of thumb, 1 inch diameter for 1 foot of depth. And then for antenna frequency limits, a high frequency antenna provides really good resolution, but less depth penetration. So sometimes that concrete scanning, you may get great resolution, but only to 12 inches. So the opposite is also true for low frequency. You can detect, you've got better depth penetration, but less resolution. So these are situations where you're probably looking for something pretty large that's pretty deep below the subsurface. And then interference, it's not common, but it is possible. I've only encountered this situation twice, and both of them happen to be on DoD installations, which were using high-powered radar systems. So, we're using radar frequencies, and if, another device is using a similar frequency, that can interfere with the data and cause noisy data harder to interpret. And then terrain and vegetation, GPR systems should be ground coupled. And what I mean by that is that the sensor itself should be touching the ground or as close to it as possible. And the reason for that is you want to direct all that radar energy directly into the ground to get as best results and resolution as possible. So you've got uneven terrain or dense vegetation that may affect performance. And so, if it's vegetation, that's oftentimes something that we can mitigate in advance by mowing or, removing that vegetation to the best of our ability. Sometimes there's nothing you can do about terrain, but if, we're on a project site where we can level that out, we should try to do that to get really good data. So how does GPR increase safety? This is a clip from a ARC News article, which basically says, estimates are that a utility strike occurs every 60 seconds in the United States. This can result in estimates of 50 to $100 billion of cost added to the US economy every year. So we can increase safety by reducing utility strikes. We can identify unrecorded lines. Oftentimes I've seen contractors, when they do have a utility strike, they're relying on utility maps that may be outdated or incomplete. Just as an example, I know ECC, we do a lot of work on DoD installations. There's not been a single DoD installation that I've done GPR on where their utility maps were accurate. So keep that in mind as we plan our project sites. And then, of course, we can detect voids in advance to prevent a collapse for bringing heavy equipment. We can keep our employees that are digging safe by locating live electrical or gas lines to prevent explosive risk. We can use GPR to improve our confined space and excavation planning, which also enhances our pre-task hazard analysis. So all of these things can increase project safety on ECC project sites. So why should we care? Obviously safety is number one, but sometimes we're required to do this. Our project specifications. This is an example from our Wake Island project. This is an active project out on Wake Island. This is an example of the specs right out of the document. I had reviewed this and highlighted some things. This last sentence here, the use of historical drawings does not alleviate the contractor from meeting this requirement. That's because they know that these are often incomplete or out of date drawings. There's many iterations of utility work that happen over several decades, and not all of that makes it to the final record keeping. Of course, our commitment to employee safety, we want to make sure that we know what we're digging on before we start. And then mission critical infrastructure. Again, we work on DoD installations. You can imagine, for example, that, say we're working on the Missile Defense Agency site. and we excavate and take out a comms line that was part of a mission critical infrastructure. These are big things that we need to be thinking about in advance. And of course, project delays and cost overrun associated with line strikes. So what you should know, if you're ever in a situation where you need to subcontract or plan out a GPR survey, here's some best practices when doing so. We should have ahead of time ensure that the survey area is clearly defined to the best of our ability. Any information that we can provide the GPR operator on target depth, diameter, or composition will help kind of determine the effectiveness, as well as the surface type, is it asphalt or native soil? And then we want to clear and demarcate the survey area ahead of time. This image here shows an example of that. Again, this is a GPR survey that we did out in Guam. The prime contractor clearly laid out in whites where they had intended to excavate, which made our job a lot easier, which just showed up very efficient. So we want to do that ahead of time, clearing vegetation, moving obstructions to the best of our ability. And then sometimes we want to verify the insurance coverages and contract language. Oftentimes, if we're subcontracting a third-party utility locate service, they're going to have contract language that tries to absolve them from any liability or risk, just due to the simple fact that sometimes utilities are not detectable, so they don't want to take that risk, and we need to understand what that risk means for ECC. And then lastly, use ECC subject matter experts like myself if you need help. Reach out. I'm always happy to talk through some GPR surveys, design, or what may or may not be feasible on your project site. And ECC, we own 2 GPR systems internally, so we can also perform some of these surveys depending on location, resource availability, etc. And which ECC divisions should use GPR? I have all of them here. I can imagine a scenario where every single one of these could use GPR surveys on their project sites. And that's it. I'll take any questions if there are any.
I don't see any in the chat. Feel free to come off mute, everybody, if you have a question. All right. Well, I will include a link to a recording of this session again in the chat, along with your attendance quiz. Please be sure to take that quiz as soon as possible so we can capture your attendance for today and keep you up to date with your compliance.
Thanks very much, Jeremy. Good job.
Yeah, thanks all.
Thanks so much.